So this chapter is entitled Thermodynamics because it is dealing with the type of energy exchange that's more important in benchtop chemistry and chemical reactions that are happening, say, in a hood or on those benchtops you think about when you think of our Chem 1 labs. Um, because of that, we only really tend to have heat exchange. And so in order to actually discuss this type of heat exchange, we need to actually look at how can we calculate and quantify the amount of heat that's changed or moved between different systems. And so just to start this discussion off, I want to ask a question. I want you to think about this, and if you want to pause the video, go ahead, but I'm going to continue on. When I ask a question, just which of these two houses got two houses, or a picture of two houses pulled off YouTube, Google long time ago? Um, would you think would cost more to keep cool, say if you're in the summertime? Say you at one point you have say your house. Apparently you got 4 stories, but your house someplace in near the city, and then you got your beach house. Which one's going to cost more to cool in the summertime? And the answer you probably know. I mean, I'm sure every time I ask this in class, like everybody, or a lot of people raise their hands, and everybody always gets it right. The, the larger house is going to cost more. You just know that intuitively. You got a bigger space, it's going to take more to actually cool that thing. Why is that? Even though if we're setting both of these, say, to a very comfortable, you guys may not think this, but a very comfortable 78 degrees Fahrenheit. So setting them both to 78 degrees Fahrenheit when the outside is, say, 90 degrees Fahrenheit, we're going to have to change the temperature by 18 degrees in both cases. But you know that it's going to cost more to actually keep this one at 78 degrees Fahrenheit. You just know it. And why is that? Since the temperature is actually it's the same. And the answer is because it takes a different amount of heat to be transferred to change the temperature of these houses. And so this relates us to what we call a heat capacity. So a heat capacity relates heat transferred, a total amount of energy, think in joules, divided by the temperature change. And so what would we say? Well, if it would take more joules to exchange the heat for this thing, say we were wanting to warm it from 78 to 90, we would have to add more joules. Then that means that this thing would have a higher, larger heat capacity. So every object has its own heat capacity, and it's pretty consistent for the object. It's mostly based on the mass of the object, and so larger things have more mass, but it also is based upon the type of material the object is made of, or in this case, materials that it's made out of. And so the general equation for heat capacity, notice this is a C, and there's no subscripts, so C with no subscripts as heat capacity is Q, that is our heat from, remember, delta E equals Q plus W. That is that same Q right there. And then we got delta T over temperature change. This is an equation that's good to know. There might be a question, but it's a little less likely for the exam. But it's good to know this equation. What's more important is actually a thing we call specific heat. Specific heat. And the reason why is because this is, it's called specific heat, even though this is specific to this house. This house would have a certain heat capacity. Specific heat is specific to material type or the chemical composition. And so in chemistry, one would have a more general kind of equation. Even though it's called specific heat, it's actually a little bit more general, that is general to a type of chemical. And so specific heat, this C sub S, notice that's for specific, has a slightly different equation. This is the same as C, but we have this other thing that is a mass term. So this term, mass, is actually makes it more general, because all we have to do is we have this a specific heat, is actually related to the amount of heat that's exchanged to change the stuff, the material's temperature. So we got a delta T, but then we have to know how much of the material we have, and we do that by mass. A lot of times this equation will be rearranged to actually solve for Q. So again, you're doing the math, right? We would multiply both sides by M and both sides by delta T. And I've just rearranged it where Q's on the left. And so this is the heat transferred times the mass of the object times the specific heat of the material, mass of the material, I should say, times the specific heat of material times delta T would be equal to the amount of heat transferred. Now, the reason why we rearrange it for this like this is because mass is something we can measure. Specific heats have been measured for many, many types of material, and then change in temperature is something we can measure fairly easily. So we can measure this pretty easily, and these we can find in tables. And so we often are using this to find the amount of heat that's transferred. Now notice, look at all these specific heats. I just want to kind of give you a qualitative thing. Notice water on here has the largest one. What does that mean about water? It means that it takes more energy to change the temperature of water than it does for any of the other materials listed here. Water has an incredibly high specific heat compared to many, many other things. And there's some important applications of that. So how would we use the equation? Well, I've got an example on here. And there'll be a couple of examples in the Chem 101 assignment. Not examples, problems in the Chem 101 assignment that are related to this. But remember, when you're doing these problems, think about which of these things you actually have and which ones you need. So my example here is find a penny that's minted before 1982, and this is because pennies are nowadays have like a zinc core and some other materials in them, just the copper coating. But if it is an older penny before 82, they were actually very, very close to pure copper. And imagine you got it and you're outside and there's snow. I know that's probably not going to happen in Southwest Florida, but let's just say, you know, you're going someplace for a vacation, next fall or Christmas, and then you got this thing, and the snow happens to be below freezing, okay? Because otherwise, if it was above freezing, it'd melt. If it was at freezing, there would be some water too there, most likely. The temperature of your body is 37 degrees Celsius. That's just normal body temperature. And we're going to assume that the penny is pure copper again because it was before 1982. And we're going to ask how much energy was transferred in order to warm it up to your body. So how much heat is absorbed by the penny as it warms from the temperature of snow to your body temperature. So if we're looking at this, right, we're going to want to actually calculate for heat. That is the value of Q. So we actually already have the Q equals mCs delta T, right? So that was the form we saw at the bottom of the last slide. Now we're going to start plugging in things. So we will have to do Q equal to the mass of the penny. So our mass is given in 3.10 grams. Then we have a specific heat. Well, we're told it's copper. So notice I have a table here for me. I have none of these memorized, except actually I do have the water memorized because we use it so much. But I have none of these other numbers memorized. And so if I don't expect me to know it, I won't expect you to know it. Even the water I give to you on an exam. And then we would put in the specific heat of copper, 0.385. I'll go back. 385. Notice the units here. Joules/gram degrees C. I'm going to write it slightly different way. Joules over gram degrees C. And if you want to actually put a 1 here, because it makes, you want something in the denominator, a number in the denominator, that's fine. And then we have delta T. And so remember, we want to do delta. Delta means final minus initial. And so in order to put this in, well, if the temperature is warming up to our body, or the penny's warming up to our body temperature, we would put the final here, and then minus the initial. 8.0 degrees, except I made a mistake. Look at that. I got the final, but this is a negative value right here. So it's a negative negative. Remember from mathematics, that means that that thing would end up being a positive value. Let me put another parentheses in here so I have the right number. And so this is our calculation. So if we go through this, 37 minus a minus 8 would be 37 plus 8 for the total change in temperature of 45.0 degrees C times 0.385 times 3.10. Now I just got Q is equal to 20.4. Following along on your calculator, I hope you got that because I'm going to double check my calculation because that is not right. I think I got it wrong. So 45 times 0.385 times 3.1. Yeah, this is not right. Q is equal to 53.7. And now if we're looking at these things, we actually want to look and see we got grams and grams canceled. We got degrees Celsius canceled with the degrees Celsius there. And notice all we have left is joules. Well, what were we trying to find? The amount of heat that was absorbed. Heat is an energy and joules is an energy. So we have the right unit. So go ahead and try out Chem 101. This would actually be the second set of questions. So again, remember we're in chapter 10. So look for the homework. Chapter 10,